Have you ever wondered why water molecules are, always bent and never straight? Or how carbon atoms manage to build these incredibly complex structures that make up, well, everything alive? The secret behind all of this molecular architecture, the reason molecules have these specific, predictable 3D shapes, it all comes down to one powerful idea: molecular hybridization.
So let's start with the big question here. Why don't atoms just, clump together randomly? Why is it that a water molecule is always bent, but carbon dioxide is always perfectly straight? It's a great question, and it's exactly the mystery we're going to solve today.
And here's the answer. It's this really elegant concept called hybridization. Honestly, the best way to think about it is like a recipe. An atom takes its basic ingredients, these things called atomic orbitals, and it literally mixes them together to create a brand new set of what we call hybrid orbitals. And these new orbitals are the things that dictate the final shape, the geometry of the entire molecule.
Okay, so to really get a handle on this recipe, we're going to start with the simplest ingredients out there, the s and p orbitals. Let's just see what kind of shapes we can cook up by mixing these two.
All right, recipe number one, the simplest one we've got. We take one s orbital, that's the spherical one, and one p orbital, which is kind of dumbbell-shaped. We mix them together, so what do we get? We get two brand new, totally identical orbitals called sp hybrid orbitals. It's a perfect trade. 2 in, 2 out.
And check this out. If you look at what these new orbitals are made of, it makes perfect sense. Since we mixed one s and one p, each of the new sp orbitals is a perfect 50-50 blend. It's got 50% s character and 50% p character. And that exact balance is what's going to tell us what shape it makes.
So the question is, how do these two new orbitals arrange themselves around that central atom? Well, like all things in nature, they want to get as far away from each other as possible. So what do? They point in exactly opposite directions. And the result? A perfectly straight line.
So there you have it, our final product. This arrangement gives us what we call a linear geometry, with the atoms all lined up in a straight line. That means the bond angle is a full 180 degrees. A classic example of this in the real world is beryllium chloride. You've got the beryllium atom right in the middle, using these two sp orbitals to grab onto a chlorine atom on either side.
Okay, that was pretty straightforward, right? So what happens if we toss another p orbital into our recipe? Now we're mixing one s orbital with two p orbitals. And you guessed it, the rule's the same. The number of orbitals you put in is the number you get out. So we end up with three brand new identical sp2 hybrid orbitals.
So now we've got three things trying to get away from each other. How do they do it? Well, they spread out into a flat triangle. This shape is called trigonal planar, and it has a perfect 120-degree angle between each bond. If you want to see this in action, just look at boron trifluoride. You've got boron in the center, bonded to 3 fluorine atoms in this perfect triangular shape.
All right, now let's build on what we've learned and look at one of the most important shapes in all of chemistry. I'm talking about the blueprint for methane. This is a total cornerstone of organic chemistry, and it's all built using something called sp3 hybridization. Okay, so for this recipe, we're using everything we've got in this particular shell. We take our 1s orbital and we mix it with all 3 of the available p orbitals. We're throwing them all in. The result? 4 new, perfectly equivalent sp3 hybrid orbitals.
And if we look at the character breakdown, you'll see the pattern holds up perfectly. We used 1 s and 3 p's, that's 4 orbitals total, to make 4 new ones. So each of those new sp3 orbitals is 1 part s and 3 parts p, or, 25% s character and 75% p character.
So how do 4 things spread out in 3D space to get as far apart as they can? Now, you might think they'd form a flat square, but they don't. Instead, they form a tetrahedron. This is a really fundamental 3D shape, kind of like a pyramid with a triangular base. And the angle between any 2 of those bonds is this very specific number, 109.5 degrees. This is the exact structure of methane, and I'm not exaggerating when I say this tetrahedral shape is basically the backbone of almost all the organic molecules that make up life itself.
So far, we've only been playing with s and p orbitals. But to build bigger, more complex molecules with more connections, we've got to bring in the heavy machinery. It's time to start mixing in the d orbitals. So our first venture into this new territory involves mixing 1s, 3 p's, and now 1 d orbital. That's 5 atomic orbitals going in, so you know what that means.
5 new sp3d hybrid orbitals coming out. And this combo creates a really cool shape called trigonal bipyramidal. You see this in molecules like phosphorus pentachloride.
Now this is where it gets really interesting. Unlike all the other shapes we've seen, not all the positions here are the same. You've got 3 orbitals making a flat triangle around the middle. We call those the equatorial bonds, and they're 120 degrees apart. But then you have 2 more orbitals sticking straight up and straight down, above and below that triangle. Those are the axial bonds, and they're at a 90-degree angle to the triangle. So you've got 2 different bond angles in the very same molecule. How cool is that?
All right, let's push this just one step further. What if we add a second d orbital to the mix? Now our recipe is 1 s, 3 p's, and 2 d's. This combination gives us a total of 6 sp3d squared hybrid orbitals. And these 6 orbitals arrange themselves into this incredibly symmetrical, really beautiful shape called an octahedron. A perfect example is sulfur hexafluoride.
And the beauty of the octahedron is its absolute perfect symmetry. Remember how that last shape had 2 different kinds of positions, the axial and equatorial? Well, here, forget all that. Every single position is identical. The angle between any 2 bonds next to each other is exactly 90 degrees. It creates this perfect, uniform, 3-dimensional structure.
So, we've just walked through all the fundamental recipes for building molecules, from the simplest to the most complex. Now we can take everything we've learned and put it all together into one single, comprehensive cheat sheet. This is where we connect the recipe directly to the final shape. And here it is, the ultimate cheat sheet. This table lays it all out. Just look at the logical progression. As we add more orbitals to our hybridization recipe, the number of connection points, what chemists call electron domains, goes up. And as that number goes up, the geometry changes in a totally predictable way. We go from 2 domains with sp hybridization giving us a line, to 3 for a flat triangle, 4 gives us that all-important tetrahedron, and on and on. The pattern is so clear, and it continues all the way up to mixing in 3d orbitals, which gives us the 7 domains we need for a pentagonal bipyramidal shape. This is literally the complete blueprint for predicting how molecules are going to look.
So let's just bring this all full circle by going back to that core definition. At the end of the day, hybridization is just the process of mixing these basic atomic orbitals to create new ones. And these new ones perfectly explain the bonding and, crucially, the 3-dimensional shapes that we actually see in molecules. It's the theory that makes all the shapes make sense. Okay, so we've pretty much uncovered the how and the why behind molecular shapes. But you know what? This just leads to the next, even bigger question. Now that you understand the blueprint, how do you think a molecule's specific 3D shape, its geometry, affects everything else about it? You know, its properties, its function, how it behaves out in the real world. That's the next puzzle to solve. Something for you to chew on.